and logarithmic functions. The two go together. We'll talk about and introduce this week, today, logarithms. And if you have not seen that before, it is a different kind of math, but it is based on exponents, based on the laws of exponents. So it's a fancy way of dealing with exponents. So first, the definition of exponential functions. Here, the exponential function given as f is said to have a base b, is defined as f of x equal to b to the x. So we say that that f grows exponentially as x increases. And one thing you want to note about just the requirements for b, and that is that b has to be greater than 0 and b cannot equal to 1. What happens if b is equal to 1? Then basically all you have is just 1 raised to various powers, which technically would be 1. If you're in the space that we're in now, the world that we're in, I guess you could say, math has several spaces. There are other complex spaces in functional analysis and so-called real analysis where you have spaces where 1 to the infinite power actually means something. And so you have to kind of go and chase the rabbit, if you will. But that's the reason here where b is not equal to 1, because if b is equal to 1, then you have f of x is equal to 1 to the x. And that kind of looks like 1, 1, 1, and here x is any real, so I mean, those values could even be negative, -1, +1 if x is -1. Doesn't matter about x. If x is positive, then we get 1 to the positive value, which is just 1. If x is negative, then we have 1 to the, say for example, the negative first power, which is still 1. And then if x is 0, but here notice the requirement that x cannot equal to 0. If b is 0, excuse me, then you get 0 raised to a power, which we don't define that based on where we live. So we get all these values of 1. So we exclude b equal to 1. And that's the reason why. Well, what we're going to do with the exponential form is kind of flip it, kind of look at it a different way, and then we'll just call it a logarithm, but then we'll define it in very strict definition, and we'll show you that in just a moment. If you take the graph for the function 2 to the x, and what, just intuitively, you can plot just a few points here listed. They've plotted 1, 2, 3, 4, 5, 6, 7. 7 of those points just to kind of, plot them on the XY plane and see how that graph is looking. You can probably get away with that by maybe plotting 4 or 5 of those points to kind of see how that looks. We won't do too much graphing in chapter 3, so you'll be thankful for that, right? But that's just the basic graph there for 2 to the x. If it's 3 to the x or 5 to the x, they're going to all still have this basic shape. Now, it's interesting that you see this number here, this 1 over 2. Here, if that's the base, so basically here we're saying that b is equal to 1/2. You can think about that as being 2 to the negative first power, if you remember those laws of exponents. And so what this comes out to be is g of x is equal to 2 to the negative x power. So what that does is kind of reverses the graph from 2 to the x. Here you got 2 to the x. See how this graph is going this way. And then over here, we basically get 2 to the negative x, and this graph is just somewhat, I suppose you could say, symmetric there. And that's what's happening. So just want to show you that, and they do the math for you as well there. And so this value for b, see here, this b is equal to 1/2. Remember that b has to be greater than 0. That's how it's defined. Let's go back and look. So that's the definition, right? That b has to be greater than 0. Well, if we take b to equal to a number, a fixed number, if b is equal to e, this natural base, number, one of the transcendental numbers, a number that is said even by the ancients to have divine properties. Here, e and also pi, to name 2 of the transcendental numbers that we commonly run into. That number is actually found by this limit, and you will deal with that in calculus. So the limit of 1 plus 1 over n to the nth power as n increases, exceedingly, as n goes to infinity. That number comes out to be, just even on your calculator, and I did not bring my calculator, and we'll need one, but maybe I can get your assistance to help us out. On your calculator, you have that number e. See if you can pull your calculator out and see if you can calculate that. It should be e to the, you're going to find that e base. It's going to look like maybe e to the x on a calculator button. If you find that, you're going to put in 1. Hit that button, put in 1. Depends on what kind of calculator you have. You may have to put 1 first and then press that, or press this button and then press 1. I don't know. If it's a Casio, it's a little bit kind of backwards than the Texas Instruments and that kind of thing. Did you get that number 2.71828 on your calculator? Okay, very good. Michael, you got it?
Yes.
Okay, good. That's good. And that's going to be just very helpful here in this chapter, just kind of knowing where those buttons are. So you do the math, the algebra, but then you get down to the bottom, and then you have to use a calculator to actually get the number that you want. And so, all right. So logarithmic functions. These are our objectives today. Change the form of logarithm to exponential. We'll see how that looks like. That's going to be based on the definition of the logarithm, and I'll show you that. That definition for the logarithm, you want to just memorize it and just kind of carry it with you, forever. So, if I wake you up 3 o'clock in the morning and ask you, what's the definition for the logarithm function, you'll be able to tell me log base a of x equal to y if and only if b to the y is equal to x. So we'll talk about evaluating these logarithms, the basic properties, and then some general properties, and then here we go again with that domain, right? So we never let go of the domain, so you want to make sure you get that. Then these so-called common logarithms, and then that last objective, the natural logarithm, that's simply when we talk about the regular log, but we call the base e. If you let the base for the regular log equal to e, then we call that natural log. Well, let's look at here this definition. So what we have is that y, and we see Now that x greater than 0, that's actually your domain based on how this guy looks here. So this becomes our domain for this function. Now it changes a little bit based on how the problem is defined. If I have the log base b of x minus 5, that means that x minus 5 has to be greater than 0. So the definition that y is equal to log base b of x is equivalent. The old statement used to be if and only if. That means it's equivalent, that what is being stated over here is the same as what's being said there. So we have on one side what we call the log form, and then over here we call this the exponential form. So we have y is equal to log base b of x is equivalent to x equal to b to the y, or b to the y is equal to x. Why is the b stated there like it is here? Is because this b for that log represents the base. B is the base. Okay. So let's erase some of this stuff so you can see it. Now, the really cool thing is you want to make sure that you get that definition. This is how we used to say it, that here y is equal to log base b of x if and only if this x is equal to b to the y. Saying the same thing. But you want to kind of have something in your head where you memorize it exactly. So if I have it in log form, can I convert it to exponential form? Based on the definition, yes, I can. If it's in exponential form, can I convert that to log form? Based on the definition, yes, I can. Okay? So what are we saying? And this new math, here's what we're saying. That everything you're going to do in this chapter is based on these definitions and these properties. I have to go by that. I can't make up my new math. I can't do it my way. So that means that I need to know what is the definition, what's the property, so I can apply it. Right? So if that means that you have to have a note card and write this information down, so when you work in the problems, you can say, okay, I can apply this, I can do this. So, okay. Now, why is that important? Here's why it's important. And this is what I want you to take. One of the themes from this class I want you to take is this, is that the one thing that I learned in this class is if I'm given new set of instructions and directions to doing a certain task, I must apply those instructions and definitions to that particular system to be able to maximize the outcome. So that's on any job, any firm that you're going to be with. If it's in engineering science, here's what's going to happen. They're going to hire you as an engineer. And they're going to give you some books. And they're going to say, you got to read these books. You got to go over this information. Because this is what we go by. If you're going to be writing programs for that company, if you're going to be testing modules, in those books that they give you, they're going to have all the information you need. It's going to be basic information. It's not going to be how to do this or that. That's where they're going to hire you. But they're going to have the guidelines, the instructions, the boundaries by which you must operate. Now watch this. You can't say, I've never done this before. They're going to fire you. Because that's what life is all about. Doing things you haven't done before. So you're going to take a job and say, I can't do it. Well, you have to learn. But look, that's why you're in school. To learn different stuff. To learn stuff you hadn't seen before. And if it's new, that doesn't mean you go back and do what you used to do, because some of the stuff we used to do was wrong. And that's a lot of times why we keep getting some bad results on our tests, is because we're still applying some old techniques that we didn't master before, and you're trying to apply it to new stuff. You can't get it right if I'm applying old, wrong stuff. If you got new wine, you got to have new wine skins. So, and that's life. Let me see if I can come a little closer. If you're dating a young lady, or if you're dating a young man, you have to learn him, or you have to learn her. You have to learn what they like. You have to kind of learn their personality. That means you got to spend some time with them. You can't go in that relationship with the idea of how it used to be with an old relationship with somebody else. You have to learn the new person, right? It's going to be different. You can't say, you know, well, my other man used to, or my other woman. You can't say that. Come on, man. You know what? I mean, if you're talking like that, well, how come you're not with the old man or the old woman, that kind of thing? So, and you're going to see it. I'm telling you, logarithms is a different math. So I have to apply these new concepts, these new definitions and properties to be able to maximize, to be able to do this new math. All right. So, location of the base and exponent. Again, b is the base. You see that? Here is b raised to the y. The y is the exponent. So here, over for the log is y equal to. So you go from one statement to its equivalent statement, but they look totally different. But that's fine. They're just rewriting. So what you're going to be thinking, that if I see it like this, then you want to be able to write it in this log form. Oh, that's what that is in the log form. Or if I'm giving it in the log form, I can rewrite it in the exponential form. Oh, that's how it looks like an exponent. Okay. All right, let's move on. Here's some basic properties. Here first, the basic properties and the so-called common properties. For the basic property, that the log base b of b is equal to 1. Now, why is that the case? And if you apply the definition, the definition says that log base b of x is equal to y if and only if b to the y is equal to x. So if that be the case, then I have log base b here. This b here is representing the x, and this 1 is representing the y. So that is equivalent to the base b here of 1 is equal to x, but this is said to be x here. That's equal to here x, that's b. Well, look. Well, what's the exponent for b over here is 1. If I don't see an exponent, it's understood to be the exponent of 1. Right? Take the number 5. 5 is the same thing as 5 to the first power. Right? Why is log base b of 1 equal to 0? Well, let's apply the definition. The definition says that b to the 0 is equal to 1. Any number raised to the 0 power is equal to 1. So the two basic properties, if you don't know the outcome, this is the outcome. I'm circling. That's the outcome. If you don't know the outcome, apply its definition, you get it automatically. That's what I do. What am I saying? Let me translate. For numbers 1 and 2, I don't memorize that. Only thing I memorize is a definition. I apply the definition to a whole lot of stuff in this chapter, and I get what I need. Okay? All right. Now, you're going to look at these common properties. Again, number 1 here comes, that's the same as that number 2 up there. So we're not picking up anything new. That's that guy. And then this number 1 here is that number. Oops. Go straight. That's that guy. All right. Well, look at 3. This is log base b of b to the x. We're going to have this property that's going to say that if I have log base b of x raised to the nth power, then that power becomes the multiplier of the log. I can say n times as equal to n times log base b of x. So why is that significant? Well, here's the reason why. Because if I do that for this number 3, then that becomes x times log base b of b. But we said that log base b of b is equal to 1. So this is just x times 1, and that's just equal to x. Well, let's say if you don't remember that, let's say if you don't get that, we'll apply the definition. This is number 3. Apply the definition. Watch this. The definition says, look, here's what I have. I have log base b of b to the x. I don't know what it is. It's equal to x here, but I don't know that. I'm just going to say y. So this is if and only if the definition says the base here, b, raised to this y power is equal to b to the x, this term here. Right? So if I have the bases are the same, that means that the exponents are the same. Right? Bases are the same. You baseball and softball players, y'all ought to be able to talk to me about these bases. I'm in the right class this morning. Boy, I got the right students. Hot dog. This is a whole mama, we're cooking. So that means that y is equal to x. So here, see here I said that this was equal to y. So I can just say now, conclusively, that log base b of b to the x is equal to x. Here's what I'm saying, folks. I'm saying that most of these properties you can get based on the definition. So if you forget the properties, make sure you know the definition. All right. And then after that, once you start seeing some of these things, then you'll know what the results are. But I'm going to show you in each problem how you can get the result just by working it by hand. So look at property 4. This is the base b raised to a power. The power is log b to the x. All right. So let's say I don't know that this is equal to that. I don't know. So here's what I have. This is number 4. This is base b raised to the log base b to the x. Let's say I don't know what that is equal to y. So I'm taking the definition. The definition, why did it do that by itself? It has a mind of its own. Okay. So the definition says this. It says that y is equal to log base b of x, if and only if, that means equivalent, if and only if the b to the y is equal to x. You kind of have to get used to it, used to that terminology, that lingo. But the definition is what you want to kind of etch in your mind somewhere. So I'm going to apply the definition to this. This number 4 is already written in the exponential form. See, it's already looking like that. So I'm going to convert this guy, this statement, from the exponential form. I'm going to put it in log form. So let's see. So I got the base b, there, right? So I'm going to say that this y, that's the same y right here, right? So I'm going to say that this guy is the same thing as if I convert this. Now notice that this y here is going to represent this x over there. So this is log base b of y is equal to log base b of x, based on the definition. So if that's the case, then that implies then that here y is equal to x. Well, I said this right here was y. That means that this is x. Y is equal to x. This implies that y is equal to x. So I can erase this, and I can say, okay, that's x. That's why that's x. Okay. Well, what happens if we call the base b, if the base here a, and I'm sorry, this is from like 80 years ago where the base used to be called a, and that should have been b. If we change this base from b to e is an actual number. It's that natural number. So if I make the base e, then we say that the log becomes natural log. So the natural log is the same thing as a logarithm, just with base e. And we call it ln x, or natural log of x. All the properties for the natural log are the same as the properties for the regular log. So all those properties are still the same. All right, let's look at some problems. Okay. It says here, write the equation in its equivalent exponential form. So basically, they want us to convert this from the log form to here the exponential form. So I want to be able to see that this is y is equal to log base b of x. So notice that here the y is 2. See that? Y is equal to 2. Here the base is 5, and x is equal to 25. So this is converted to if and only if now x is equal to here the base b raised to the y power. So they want you to convert it to this. So once you know that what is y, what is b, what is x, then I can write it in this form that I have blocked off. So I'm going to say, that is to say, then, if I go by this, that here my x, which is 25, is equal to b. B is 5 raised to the y. Y is 2. And it should make sense, because 5 to the second power is indeed 25. So it's not like, you're going to get something, you're going to say, I don't know what that is. You know what 5 squared is. You know it's 25. All right. Does that make sense? And then after a while, you'll just be able to kind of get the lingo, and you'll be able to kind of move, with the flow. So, like, say, for example, if you see it, look, again, the 3 is the base. So that's 3 raised to this y here is equal to 9. So write the following equation in its equivalent exponential form. Now, basically, they want you to stop there, and you're done. Okay. Now, if we were solving, they didn't ask to solve, but if we were solving, you would look at this as 3 to the y, and then that 9 can be written as 3 to the second. And so the bases are the same, then that implies that the exponents must be the same. Y is equal to 2. So I think for that problem, I think all it did ask for was just to write the following equation in its equivalent exponential form. So for my math lab, this is all they want you to put in, my math lab. Here, let's keep moving. We're going to convert this. This guy is in exponential form. We're going to convert that to log form. So let's look at the definition again. The definition says that log base b of x is equal to y if and only if this b to the y is equal to x. So if it's written in terms of b to the y equal to x, let's just write out what we have. So here b is equal to 2, y is equal to 4, then x is equal to 16. So I'm going to convert this now to, it says write this in its log form. So this is the log form here. So this becomes log base b, here that's 2, of the 16, that's x, that's equal to 4, the exponent. Right? And you'll type that in my math lab. Okay. All right. The same thing here. Let's look at that, looking at the how the definition is set. So this is b to the y equal to x. So here the x is the 1/4, b is equal to 2, and then here y is equal to -2. So this is equivalent to the log of base 2 of 1/4 is equal to -2. You're going to type all that in there in my math lab. Okay. Now, all I've done was just to use the definition directly. And here's what we're doing, folks. And if you can bear with me with this very hard principle, and I just hope it's not over anybody's head, but I'm going to give it to you, and hopefully it'll help you out. All we're doing is just matching. Put a circle, circle, square, square, triangle, triangle. That's all we're doing. That's all math is. I know it's a hard principle. I'm sorry to put the hard stuff on you. But I don't know if you remember, like, I don't know, was it kindergarten? You know, they give you a little puzzle. You got to put that square, you know, and that square, you know. And some kids, they have trouble. I'm like, what you doing, man? It's a circle. Put the circle. You got the triangle in your hand. I don't know. And here was the thing. I could get stuff like that, but, you know, when I started like 1st, 2nd, 3rd, 4th grade, I flunked all that stuff. You know, it's like, man, school is stupid, you know. I want to go back to the square and the circle. And so then when I discovered in math that that's all we're doing in algebra, it's just put, I'm not lying. I clarify, I can't swear anymore. I made a promise. But anyway, you're just putting triangles and triangles. That's all we're doing. Circles and circles. Ooh. Let's move on. I don't have all day. Oh! Write the following equation in its equivalent logarithmic form. So let's see. Now check this out. This is the 4th root of 81. So this is really 81 raised to the 1/4 power is equal to 3. So the base is 81. So b is 81. Here x is equal to 3, and then y, the result is always the exponent. That's 1/4. Remember again, the definition said that log base b of x is equal to y if and only if, yes, that the base b raised to the y is equal to x. You want to rehearse that over in your head over and over again. You want to be driving down 565, log base b of x equal to y. If and only if, right? b to the y is equal to x. Your mama said, what is that? You say, I don't know what it is, but it's base b raised to the x equal to. No, you don't say that. So here we go. So this is if and only if. We want to write this in the log form. So this is log, the base is b, that's 81, of x, that's 3, is equal to 1/4. Now, I'm left-handed. That means that my right brain is the one that's mostly doing the functioning for me. Bless you. And so my secret is, just personally, logs are backwards to me. So the exponential setup seems to be right, but that's just how my left hand, right brain works. So it takes time to kind of, you know, get to the understanding. But sometimes I even get confused. So how to overcome that? I write it down. And I don't know, you know, maybe the new wave of learning is, you know, you can go to class, you don't have to write anything down. But I think the Lord, when he said to John on Patmos, what thou seest, write, he was putting John back in school. John, whatever you see that I'm doing, and then I'm showing you, write it down. So you write it down, you go back, look at it, rehearse it, you know, that kind of thing. Here, find the exact value of the log without using a calculator. So we're going to say, look, this is equal to y. I'm going to put this in the definition form. So this is if and only if. Here, the base is 4 raised to the y is equal to 256. All right. So what is 256 divided by 2? All right, so this is 2 times 128, sorry. All right. What is 128 divided by 2?
64.
That's 2 times 2 times 64. Very good. So now this 2 times 2 is 4, and that 64 is 8 times 8. This is 8 times 8. All right, very good. So if that's the case, this is 4 times 4 times 2 times 4 times 2. Is everybody with me? Because 4 times 2 is 8. So I have 4 to the y is equal to, let's count them up. 1, 2, 3. How many 4s do I have over there?
3.
Can I say it like from the country? I got 4 4s. Because what's 2 times 2? 4, right? So that's 1, 2, 3, 4. This is 4 to the 4th power. So do you see now that y is equal to 4? If the bases are the same, come on, softball and baseball. Man, y'all should make A's in this chapter right here. I'm going to call y'all coach and say, Coach, this is the baseball and softball chapter. They're going to make A's, Coach. And if they don't, we're going to line them up. No, we can't do that anymore. If the bases are the same, then the exponents are the same. 4 and 4 is the base, right? You see how we broke that down? Look, I just started with very small divisions. I take any number, any big number, and I always start with the very small primes. Can it be divided by 2? Can it be divided by 3? Can it be divided by 5? Can it be divided by 7? Now, why is that significant? I'm telling you, has anybody studied Alexander the Great? Alexander the Great in history. The great Greek just conquistador who conquered from Egypt all the way to China, man, and claimed it for himself. Got down to midsection of India. And I think got hit by some kind of spear and took in some kind of infection and didn't get it remedied. Thought he would kind of work his way through and died young, you know, probably not even 30. But I mean, just great military mind. But one of the aspects of his greatness in military strategy was based on his ability to understand mathematics. It was a very simple concept that he used. Divide and conquer. Divide and conquer. That's all we're doing, folks. So here, this implies that y is equal to 4. 4 is the answer. All right, evaluate this without using a calculator. All right, no problem. Now this is log base 5 of 5 to the negative first power. You remember you got a property. There was one property that said that log base b of b to the x is equal to what? X, right? So this guy here is equal to -1. But what if you forgot that? So the answer is -1. But what if I don't remember the property? answer, apply the definition. All right, so the definition said again, log base b of x equal to y if and only if base b of y is equal to x. So here, if I have log base 5 of 1 over 5, let's say is equal to y, that's if and only if 5 raised to the y is equal to 1 over 5. Now I need to convert 1 over 5 to the base of 5. Well, that's the same thing as 5 to the negative first power. So now, since the bases are the same, 5 is the base, so the exponents are the same. That means, implies that y is equal to negative 1. So if you remember the property, fine. If you forget the property, make sure you know that definition. All right. So I'm going to use the definition. This is equal to y if and only if the base, which is 32, raised to the y is equal to 2. The only way that I can get that is that I have to manipulate the 32. I have to write the 32 as a base of 2. I know that 2 times 2 times 2, whatever, should give me 32. I think it's 2 to the 5th power, right? 2 to the 5th power is equal to 32. That is 2 times 2 times 2 times 2 times 2, 5 of them. That's equal to 32. So that is to say, this is 2 to the 5th power raised to the y is equal to 2 to the 1st power. Remember from the laws of exponents, if I have a power raised to a power, we multiply the power. So that's the same thing as 2 to the 5y. This implies this is 2 to the 5y is equal to 2 to the 1st power. The bases are the same. All right? The bases are the same, so I set the exponents equal. 5y is equal to 1. This implies that y is equal to 1 over 5. So that's equal to y, that's 1 over 5. Now note, here's how we took that 32. It's 32 is equal to 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5. That's 2 to the 5th power. And then we also made use of the law of exponent, that if I have x to the n raised to the mth power, that's equal to x to the n times m. A power raised to a power, I multiply the powers 5 times y. A power raised to a power, you multiply the powers. Okay. All right, evaluate this guy without using a calculator. This guy is in exponential form. The base is 4. So I'm going to say, let this equal to y. Now remember the definition said this, that log base b of x is equal to y if and only if b to the y is equal to x. This guy is already written in the form of b to the y equal to x, right? But here this is b to this guy, which is that y is equal to here y, but that's said over here to be representing the x right there, right? So let's see if we can identify without confusing you, because we got a kind of mixed terminology with the x and the y. All I'm saying is this, that this looks like this. That's what I'm saying. I'm matching them up. So then I wanna write its equivalent form, put that in the log form. So that's gonna be log base, here b is 4, log base 4 of y is equal to log base 4 of 2. So this implies that log base 4 of y is equal to log base 4 of 2. Well, if I have the log is equal to the log is equal to a log, and they have the same bases, that means that this is the same as that. Y is equal to 2. So this implies that y is equal to 2. So the answer is 2. Okay. Find the domain. Well, no problem. Remember, we talked about the definition that y is equal to log base b of x. With the domain here is that x has to be greater than 0. Whatever is here. Now, please understand, in your life with algebra, x just represents what's there, right? So here, what's here for this problem is the x plus 6. So here, this implies that x plus 6 has to be greater than 0. Get the x by itself, that is that x has to be greater than negative 6. So our domain is not equal to, parentheses, negative 6, all the way to positive infinity. That's our domain. Does that make sense? All right. Again, I'm going back, man, I'm just killing that definition. I'm just working on that definition. That's all I'm doing. That's all I'm using. That's how I got it. How did I get it? I can't keep too much stuff in my head when I was coming up. So if you can give me one thing, can I work everything on that one thing? Sure can. I even applied it to life. It was just I only had one verse to go on in the Bible. I want to apply this one verse to my life. Genesis chapter 1, verse 1. In the beginning, God created the heavens and earth. I'm through. I just take that. I'm good to go. I'm good to go. Whoa! Whoa! Okay, we gotta keep moving. Okay, be quiet, Ernest. Okay, evaluate the expression without using a calculator. All right. So here, 10 is called the common base. The common base is 10. Sometimes not written. Okay. So that is log base 10 of x is the same thing as log of x. Okay. So if you don't see the base, it's understood to be the common base of 10. So for this problem, this is log base 10 of 1,000. And again, there's a couple of ways you can do it. You can use the definition if you want. But if you get the property, look, this is log base 10. This is 10 to the third, because 10 to the third power is equal to 1,000, right? So if the base is the same as this number here, if it's like, remember, recall, if I have log base b of b to the x, that's just equal to x, right? So this guy is equal to just 3. Okay. And look at this. This is log base 10 of 10 to the 7. What's that equal to? There was a reason now that I realized that my band director in high school used to throw stuff at us. Boy, now I get it, Mr. Broadnax. You know, rest your soul. You know, hopefully you, or as Fred Sanford would say, maybe. But anyway, no, this is being recorded. So log base 10 of 10 to the 7 is equal to what?
10 million. 10 million?
No, it's equal to 7, man. We just, it's the same as the problem right here above. I don't think an eraser hurt. Again, that's the property. Log base b of b to the x is equal to x. Here, the b is 10. Log base b of b to the 7 is equal to, it's going to be 7. This is an exponential form. I'm going to write it As such, this is equal to y. Based on the definition, I'm going to put this in log form. So this becomes log base 10 of y is equal to log of 33. My question now is, what is y equal to? 33. Again, if the base is not written, that means it's the common base of 10, right? So this is the same thing as log base 10 of 33. So the positions match up. Why? It's algebra, man. They're equal. So y is equal to 33. So you're finding that without a calculator. All right. What about this? Check this out. This is the log of base e to the 1. Now I'm going to show you why this result is 0. I'm going to show you that, because if you base this on the definition and say this is equal to y, if and only if, let's apply the definition, this is the base e to the y is equal to 1. What does y have to equal such that e to the y is equal to 1? What about this? Okay. What's 5 to the 0 equal to? Huh?
1.
Yeah, I was going to go back to the farm. Ah! Good, right? All right. What is 18 to the 0? 1. What is house to the 0? 1. Equal to no house, right? All right. All right. So what is e? If e to the y is equal to 1, then this implies that y has to be what? 0. So anytime I see the natural log of 1 here on out, that's going to be 0. See that?
Your house is missing a chimney.
I have gas. No chimney for me. I had to cut too much wood when I was growing up because our house, the only way we could keep warm was to burn wood. We didn't have any inside heat, nothing like that. So it was funny. We built the house in 2003 in Madison, and so the builder was like, "Do you want a fireplace?" I was like, "Heck, no, man." So, but we've moved on, and the house we have now has a fireplace. But I was just still brain shocked from just growing up suffering from. It was a necessity that you cut wood and you burn that wood in that house if you want to keep warm in the wintertime, and that was pretty rough. But I thank the Lord for my journey. Evaluate this expression without using a calculator. The natural log of e to the 4 is equal to what? 4. Very good. That's the same thing. Look, this is log, this here, of base e of e to the 4. Remember, that's the same thing as log base b of b to the x. That's equal to x, right? All right. Let's look at this guy. This is the natural log of e to the, is that just negative third power? Do you see that? 1 over e to the third. It's the same thing as e to the negative third, because that's a law of exponent, right? Recall that, right? X to the negative n is the same thing as 1 over x to the n. Do you remember that? Right? Math 100. Matter of fact, also Math 098. So even if it's what's on the right side, it's still equal. So if I'm given 1 over x to the n, I can write that as x to the negative n, right? So if I'm given 1 over 5 to the 4th, that's the same thing as 5 to the negative 4, right? So if this is the case, then what's the answer here for this problem? Negative 3, right? All right. Oh, by the way, the natural log and the e base are inverses of each other. The natural log and the ln and the e base, they're inverses. So if the inverse is pretty cool. If you put them both together, that means that the result is going to be whatever the term is that you have left. So I can write this in, convert this from exponential to log form. But if I understand something about the inverses, that the e to the natural log, they somewhat cancel out because the inverses, so my result is 116. That next one, e to the natural log of 3x squared, the result is 3x squared. So here, this is just equal to 116. Nope. E base and natural log of x are inverses of each other. So if I do the composition, you remember the composition from those inverses, f composed with f inverse of x was just equal to x. Now, what if you don't see that? No problem. This e to the natural log of 116, that says equal to y. Use the definition. This is if and only if the log base e of y is equal to this natural log of 116. We said that the log of base e is the natural log. So this is the natural log of y is equal to 116. Well, that implies that y is equal to 116. Okay. So here, and here's the cool thing about math. Once you get it, you work one problem. If I see any other problem in that same form, the result's still the same, right? So you see how this first problem and that second problem, they're the same problem. So here I know that this is going to be 3x squared. You see that? All right. Solve this without using a calculator. Remember, if there's no base, it's understood to be the common base of 10. So now if I have 10 raised to the log base 10 of something, the result is that something. Matter of fact, it don't have to be 10. It could be 5 raised to the log base 5 of something. The result is that something. As long as this base here is the same as that base, this is the result. Well, let's say if you don't know that. Okay, this is equal to y. So now I'm going to apply the definition. This guy is already written in the exponential form. So we said this is if and only if. I'm going to put it in log form. This is log base 10 of y is equal to log base 10 of the square root of 14x. So that means that y is equal to the square root of 14x. That's the answer. Okay. All right. Here, write the equation in its equivalent exponential form and then solve for x. All right, no problem. What is the exponential form for this problem right here? We say that this if and only if. This is written in log form. What's the exponential form?
2 to the 3rd power equals x minus 3.
I love it. I was gonna say, let my hand be your hand. Maybe a little darker, but that's all right. We're all brothers and sisters. Okay, well, very good, Kaylee. So let me ask you this. What's 2 to the 3rd? 8. So this is 8 is equal to x minus 3. So now it's just algebra. So now that means that 8 plus 3 is equal to x. So x is equal to 11. All right? Again, all we've done was to apply the definition. We're given something that was written in log form. I converted it to exponential form. Look at it. Can I reduce that to my hometown of math? And we just did that. Right? Let's look at another one very similar. All right. See if you can work that one out. Let's see what you get. Ma'am,
It's 5 negative 2 equals x.
you better believe that. And so then simplify that. What's x equal to? Why are you looking like that, Michael? Huh?
1/25.
That's right. Yep. I've been everywhere, man. So you said 5. Tomorrow you said that negative 2 is equal to x. Based on that, that's a law of exponents with that negative. So this is 1 over 5 to the second, which is 1 over 25. Okay. Very good. Any questions there?